Next up, we're thrilled to welcome Drago Anguelov. Drago is the head of research and a distinguished scientist at Waymo. He leads the research on pushing boundaries of autonomous driving using machine learning. Prior to joining Waymo, Drago led the 3D perception team at Zoox. Before Zoox, Drago was at Google, first working on 3D vision and pose estimation for Street View, and later leading a research team which developed computer vision systems for annotating Google Photos. The team also invented popular methods such as the Inception neural network architecture and the SSD detector, which helped win the ImageNet 2014 classification and detection challenges. Drago, over to you.
Hi, I'm Drago Anguelov. I lead the research team at Waymo, and today I will tell you about how we leverage machine learning to build our autonomous driving stack. A short intro for those that are not familiar with Waymo. We are Alphabet's autonomous driving company. We are building the world's most experienced driver and focusing on two categories, moving people with our Waymo One service and moving goods with Waymo Via, our commercial delivery arm that features these Class 8 trucks and delivery vans. Over more than a decade, we have driven over 20 million miles on public roads in autonomous modes, over 20 billion miles in simulation, and across more than 25 cities in the United States. And all this experience that we have collected is benefiting all the drivers in our fleet. Since October 2020, we have been offering Waymo One, the world's first fully autonomous service, with 100% of rides currently with no human driver in Phoenix, Arizona. Waymo One riders are now able to hail a passenger vehicle on the app when they download our app and invite guests to join them and tweet and blog about their experiences on social media. And let's see what some of their experiences have been like.
Hey guys, my ride is here. Here we go. Check this out.
Your name, Kyle. This car is all yours with no one up front.
Oh, wait a minute. How come we're going red light? Oh, we're turning right on red. Ah, how about that? Right on red. Boy, he gets with it, doesn't he? He steps on the gas pretty good. Or she, it.
See? No one up there. So crazy.
Yes. Let me tell you why. We've been doing this since 2018 when they had drivers in the front seat that could manually take over just in case. So yes, I'm quite comfortable with this.
Work zone, speed limit 35. Yep, and nailing that 35, no problem.
Thank you.
Alright, we're coming to a stop sign. Let's see what he's gonna do. Oh, adjusting. Getting ready. Hey, whipping it. This car drives better than some of y'all!
So this is some of the experience people have been having with our first and only autonomous service currently open to the public. And we're working hard to keep improving the service and, of course, to bring it to a lot more places. In more recent news, earlier this year, we announced that we have significantly expanded our testing in San Francisco. And last month, we announced that we have kicked off our Waymo One Trusted Rider Program, Trusted Tester Program. It allows San Franciscans that are part of the program to hail an autonomous ride of our all-electric new platform based on Jaguar I-Pace and featuring our 5th generation sensors and get rides in the city. This new 5th generation sensor suite of ours includes powerful state-of-the-art lidars that can see up to 300 meters, cameras with very high resolution that can see even longer range, 360 degrees around the vehicle, and see around occlusions like in the front pods on the side, And we have a radar imaging system that offers great field of view and resolution compared to any in its class. So before I show you our Waymo Driver handling some San Francisco streets, I want to do autonomous vehicle driving 101 introduction to describe roughly what the stack needs to do in order to be able to drive safely on the street. And this is to benefit people that are not that well familiar with our autonomous vehicle driving domain. And so imagine you're at this intersection that I'm showing you. And the first question the system needs to address is what is around me. It can leverage our rich suite of sensors and potentially some prior map knowledge, and detect a set of agents in the scene, the police car in front, the various vehicles, pedestrians, and also detect traffic lights, various other map elements, construction, and the like. And so once we have done this, the next question to ask is, well, what is likely to happen next? This involves predicting the behavior of other agents. What are they likely to do in the scene based on the context and some of their current actions? And given that we have these predictions, the next question is, what should I do? It's about deciding how to make progress in the scene. And that is planning. It requires planning a trajectory that is safe in this environment. And let's say we pick this green trajectory, then ultimately a controller executes the necessary steering wheel turns, throttling and braking to take us on that trajectory, right? And so these are all the tasks that an autonomous vehicle needs to do. Let's see some examples from us doing fully autonomous driving in San Francisco. So this is in autonomous mode. You can see on the top right, there's a green square saying auto. And here you can see some interesting interactions in dense urban scenarios, or even in these narrow streets. There's a lot of interactions that we need to be able to successfully handle. Here we're negotiating in a narrow street with another vehicle going over a bump. Before we had a bicyclist signaling to us. Here a pedestrian really wishes to go in front of us, and we courteously let him. There's a lot of busy intersections with potentially cutting in bicyclists and busy traffic that we need to pass. More bicyclist action. You can see us letting them go in front of us after they signal to us that they intend to do so. This is us driving in the night. You can see in the camera not too clear. In the LiDAR, you can clearly see the door is open, and we'll let the construction person, or is it the PG&E person, do what they're up to and then safely pass this vehicle. We can tell that this vehicle has an open door and that it's parked there for a long time. Actually, dealing with double parked vehicles is an important part of driving. Here's the more complex double parked vehicle scenarios. People loading things, we can tell, you can see by the icons, automatically we predict that all of these vehicles are parked there for a while, and so we plan a safe maneuver to go by them. Right? And so these scenes illustrate some typical scenarios of San Francisco driving. And a lot of them, as you saw, involve all kinds of interactions with agents, with vehicles on the road. Now, one of the challenges of autonomous driving and scaling it is that our driver needs to handle a variety of different scenes and domains, beyond dense urban, suburban, freeway, and of course, different kinds of weather in all of them. And that makes the problem additionally interesting and challenging. Also, the San Francisco examples I showed you are quite common. They happen all the time. There are those certain scenarios that happen quite rarely that we need to also handle well. This scenario is reasonably standard. So as we start going forward, look on the left here. There's a vehicle comes in on red and will just blow completely through this intersection, even though green was for us. And so we want to deal in these reasonably with such scenarios reasonably as well. Now, I'm going to show you an even longer long tail scenario in the next example. I think this is an example that Dmitry mentioned in his fireside chat with Alex in this conference. I will emphasize no one was harmed in this example. Let me show you what is a real rare case. So here we are starting to go. You can see something happened and blew out the trailer behind this car. So one more time. There is a vehicle coming, going by, and boom, and takes out the trailer. So maybe a closer view. Enhanced computer. So with some stabilization, you can see unmanned motorcycle plows into the trailer. Luckily, no one was injured, but events like this, even though it's hard to imagine they could happen, do occasionally happen. And even though you cannot avoid all of them, it helps to do reasonable things when such things transpire. So how does Waymo deal with the complexity of autonomous driving that I tried to illustrate to you? From its founding, we've emphasized a thoughtful and safety-conscious approach to doing this. It is also an integrated approach where we have designed our hardware and software in-house. We leverage a trio of very powerful sensors: camera, LiDAR, and radar. Specifically, LiDAR and radar are active sensors, and they're a great safety feature. They ensure that if there's some object out there, we will see it. And so also LiDAR and radar, their signal typically has less variance in the camera than the camera. For example, the shapes of cars are pretty consistent in the LiDAR, even though their appearances in camera in the various conditions can change dramatically in the pixels. And so typically you need less data in camera and LiDAR to achieve robust detection results. So ultimately, this is a great safety feature. And we have built into perception this additional attention and focus because perception is the foundation of your whole system. And if you cannot detect the initial objects or the semantic attributes of the scene, then all of your high-level reasoning beyond that point can suffer because you have not even grasped the basics. This is a short video of our 5th generation LiDAR that is on the I-Paces and the trucks. You can see up to 300 meters in dramatically better resolution with a lot better field of view, a lot more signal than our previous LiDAR stack. And it's a fantastic sensor to work with. So let's go on to the next point, which is that we also use high definition maps as a prior, not as an immutable truth. Maps are a great safety feature because they let us anticipate what happens in the occluded parts of the scene. Furthermore, the map is a dynamic entity, and it's a mechanism where our fleet can share observation between vehicles, in some cases in real time, about features that they're likely to anticipate. Maps are specifically important when parts of the scene are occluded, either by vehicles in front of you, or by a hill, or by the intersection geometry. And it's quite helpful to know what to anticipate there. It adds robustness to the stack. Also, of course, we leverage machine learning very heavily at Waymo. It's a great tool to handle the world complexity of the kind that I showed you. Of course, assuming that we have the prerequisite data to learn from, but we have this data, we have thousands of years of driving experience, and we have been capturing these diverse scenes in high resolution with multiple sensors over time. So that's great. What's also really great in our autonomous vehicle domain that some other robotics domain do not share is that when we drive, we capture the behavior of all these humans that do the same task that we're trying to perfect. You can capture 10 to hundreds of humans driving and showing you how they do it. Of course, some are real experts and some not quite so much, but it's all very useful signal for machine learning, right? At the same time, there is a requirement for robustness. You need to be able to also do reasonable things in very rare cases of the kinds I showed you. And so in that case, it does help for machine learning to be complemented with expert domain knowledge, because having machine learning deal robustly with cases when there's almost no examples is still an open research problem, right? And so an autonomous driving stack needs to be designed to leverage as fully as possible the strengths of machine learning while mitigating its weaknesses, right? And that's how we've tried to build our stack. Now, when I started at Waymo, and since then, the scope of ML has been dramatically expanding. And so by now, there is large machine learning components in every major production system at Waymo. And so each of these models benefits from cutting-edge architectures and state-of-the-art research. And for example, in perception, we have even published a lot of work in various conferences. I'll just give a couple of examples of some state-of-the-art systems that we have shown. So on the left is an object detector in LiDAR that we published this summer, running multiple times real-time on the full range of, we cut it off at 200 meters here, but on the full range of the LiDAR, multiple times faster than real-time, really accurately. This is frame-by-frame detection. I think if you combine them, you will get yet higher, smoother tracking. And on the right is a model that I'm showing called WIDAR. This is an image model. It predicts the depth of every pixel in the scene, in the images, and the uncertainty in your depth. And it also predicts semantics that I have not shown. And based on the predictions of this model, you can make a really nice, pretty point cloud. And it shows you how really well our models can estimate depth. And this state-of-the-art depth estimation that allows them to lift the cameras to 3D, it highly leverages the fact that we also have a collocated LiDAR sensors, and it helps train our camera models. And so we can get results like this, right? Now, in the last couple of years, deep learning really pushed also the state-of-the-art in behavior prediction and generally behavior modeling. And at Waymo, we have published some strong work in this space, like multipath, VectorNet, TNT. These are all various neural network architectures for behavior modeling, with increasing quality in this case. And on this slide, I'm showing you one of our more recent architectures. It's called Multipath++. It's a behavior prediction deepnet. We presented it in the summer in a CVPR conference, and it's currently the leader by a margin on our Waymo open motion dataset, and was also in the first place on another popular benchmark called Argoers for a while. So these examples I show you of this prediction model, there's various agents in the scene. We predict distribution of our possible behaviors up to 8 seconds in the future. And the darker, the more bright the colors are, the more likely the predictions are. And you can see there's some interesting intersection predictions, multimodal. And here is a parking lot with pedestrians going by and vehicles driving by and so on, right? And it gives you an idea of the kind of models we have for in these architectures for predicting and modeling behavior. And I'm showing you perception and prediction examples, but deep learning is also transforming planning, simulation, and evaluation at Waymo. We have major machine learning components in these systems in production, and I will talk a bit more about those topics later in the talk. But before I do that, I wanted to highlight a data set that we have made, the Waymo Open Dataset. We created it 2 years ago and continue expanding it. If you are interested in doing autonomous vehicle research on topics such as perception, behavior, simulation, agents, and so on, and you want to train models like the one you just saw, you may want to consider our dataset, right? And we continue expanding and enriching it, trying to make it applicable to more and more tasks in autonomous driving, and running challenges already for 2 years straight with workshop talks to highlight the winning entries. So, research in autonomous vehicle modeling is, quite an exciting field right now. And if you want to join it, or please, consider and reach out, we will continue expanding this data set. So I talked a bit about existing models. In this part of the talk, I want to discuss ways in which we can further grow the scope of machine learning in AV systems. And one promising direction is to leverage the recent large capacity model trends. So in the last couple of years, there has been dramatic improvement in the fields of natural language processing. A lot of you may have heard of this model GPT-3 by OpenAI. I think they're starting with a very high-performing transformer architecture. They showed that scaling it and training it on really large web data sets continues pushing the state of the art and the quality of the model. We see some of the similar effects in computer vision with models such as EfficientNet and also CodeNet more recently by the Google Brain teams. Again, the similar trends as the number of parameters grow for good architecture families, accuracy continues growing, generalization power continues growing. And so to me, I believe these learnings transfer to our domain. We have been collecting thousands of years of driving data with now different platforms, including trucks and passenger cars, in many urban scenarios. And in some sense, I presented this many urban scenarios and diversity of scenes and conditions as a challenge to be solved, but also it's an opportunity because now with these large model trends, handling such diverse data sets may become also a strength because models improve being fed data from potentially different environments and domains. And we're already leveraging some of these synergies and scale at Waymo now. So for example, compared to driving on surface streets in cities, truck driving is less eventful. We do it mostly on the highway. Now, we have this rich Phoenix and San Francisco data, though, and so if we leverage a lot of it for behavior prediction models, we find that we can get significant gains by mixing car and truck data. And our current, say, behavior prediction data set for trucks contains 85% of car data in a beneficial way. So that's one example of synergies across domains. And I think there's also a trend in our domain going from maybe dozens of smaller models to specialist models, each maybe trained for specific task with its own ground truth, to fewer larger models that handle and train to produce multiple outputs and benefiting ultimately from more supervision from these different outputs. And so at a more general level, if you want to summarize what recent trends are, better model architectures help, specifically model architectures that contain transformer layers do particularly well. And within a given model architecture family, quality is a function of scaled up models, but also scaled up data sets. So you can't just do one without the other. That does not quite work. So you need to work both sides of the equation, right? And so we have our fleet, very sizable with all these rich sensors that gives us a lot of data. And of course, we also have been doing research to even further augment what we can do with this data. And I will highlight a few examples of recent research that we have published. So one thing that you will see here in this video is a scene from our Waymo OpenMotion dataset. This scene was auto-labeled by an algorithm, a model that we published in the CVPR conference this summer. That model is trained and runs on offboard data, so it's not limited by latency constraints on the vehicle. And offboard, it also benefits from seeing the future, right? Because you captured the full scene, you drove through all of it. Now, for every point in time, you can look well backwards and forwards in future and estimate the most likely, a lot more accurately shaped trajectory of the vehicles and so on. And I think this clip, and I guess you can check out the data set itself, shows the kind of quality that can be achieved. And the significance of this is now we can use methods like this to go label a lot of data automatically and then train our onboard model on that data and just making it a lot more powerful as a result. Another method that is very popular for augmenting your data is, of course, applying various input perturbations. And here I've just illustrated some of the perturbations you can apply to objects to lighter point clouds. So you can scale them and drop out points and cut out pieces and so on. Now, that's all great, but you want to, these operations have a certain set of parameters. It's quite a large set of parameters. It's not that easy to guess them. So ideally, you want to automate this process. And we have a paper last year that we showed how to search through the space of maybe a dozen or several dozen parameters for these augmentations and achieve significantly higher quality and generalization for the models that leverage this technique on labeled data. And this year we expanded it to do the same kind of techniques in a beneficial manner also on unlabeled data, where we automatically label the data and perturb it to eke out maximum gains. And with techniques like this, you can potentially decrease your data needs here from black to orange is the example, maybe an order of magnitude at least, right? So that's a nice technique to have. Another technique that is very popular and relevant in our domain is self-supervision. So our models and our perception system perform multiple tasks that all contribute to a holistic understanding of the scene. In a paper jointly with Google Brain this year called Taskology, we explored some of the beneficial aspects of this rich structure in the scene. It's a spatio-temporal structure. We showed how to train potentially asynchronously in a very scalable way several different models that accomplish different related tasks. And the outputs of these tasks are related by some geometric and temporal constraints. And so whenever those constraints are violated, we can push gradient through the models and improve them to be more consistent in ways that we expect. And so that's quite effective too. I'll give you an example of what I exactly mean. So you take the computer vision scenario. If you have an image and two images, and you predict how you move between them with the model, the depth in the first image, which objects move, how they move, you essentially can reconstruct the second image given your predictions, and then you can check if in the second image the pixels look like you expected. And if they don't, you can push gradient to tell you, no, you predicted something off. Let's try to adjust all of your predictions to actually predict the next image. And that's a powerful supervision signal. It helps train a lot of outputs such as 3D flow and so on. Similarly in LiDAR, a very similar story unfolds. So if you detect objects in a frame and give their bounding boxes and velocity, you expect then in the second frame where you detect them to be consistent with the predictions from the first frame. And based on this, you can push gradient and again improve your models. So that's good techniques to have as well. And last but not least, I want to highlight a recent work of ours that will appear. It's actually an archive now, but it will appear in the ICCV conference later this year. And it's called Semantic Point Generation. And it's this ingenious idea to predict an auxiliary output in the model that can be leveraged then to improve 3D detection quality and robustness. And the way this works is we train the model first to predict these red semantic points from the black real points. And the semantic points are meant to cover the full shape of the object. And then we take this whole augmented point cloud, the real and the augmented points, and from it we predict the 3D box in the model. And so what this does, it homogenizes a lot the input to the box predictor. It helps you handle different detection cases such as long range where there's not many points because you then imagine a set of points a certain way, or in rain where the lighter patterns are different. It homogenizes the point patterns inside the model. And it also allows you to do more ingenious way of data augmentation because then now you can start transforming this augmented semantic point cloud as opposed to just the visible points. And so this method currently is tops in the Kitty benchmark. This is maybe the first, maybe still the most popular benchmark, not sure, but a good one to certainly run on. And we're first on hard and medium examples on Kitty. And this method is also tops on our own Waymo open dataset domain adaptation benchmark, which is the challenge of, okay, can you train on San Francisco and Phoenix in clear weather and then predict Kirkland in rainy weather? This type of model significantly improves the state of the art in that task. So far, I discussed approaches that works very well for the part of the system that are trained in a more supervised or semi-supervised manner. These are common tasks for a lot of domains like perception. However, in the autonomous vehicle domain, our ultimate task is to train an AI agent. And to fully leverage the power of machine learning there, it is key to be able to have good evaluation of this full driving agent behavior, which we can do ideally efficiently and without much human supervision. And that would unlock machine learning. And so a key direction to keep growing the impact of machine learning is to emphasize scalable full stack testing. Right? And how do you do scalable full stack testing? There's actually a very rich set of techniques. We have published at Waymo, the first company to do so, our safety framework in October of 2020. So if you want to learn more about testing, I refer you to that publication. However, let me recap some of the main options. So one of them is we can test our software on public roads under the supervision of a trained human operator. And so that really tests the software wholesale. You can check how it really interacts with other road users, and you can gain new experiences in the world. However, if you change your system, if you can continue driving, it may take a while for your updated system to really see some of the more rare situations. So this critical and important way of testing only scales up so much, right? And one thing that we can do to help with very rare scenarios is we can stage them ourselves. And we do so in our former Air Force base nicknamed Castle. So we have studied typical rare scenarios that from the literature that one needs to be concerned about and staged them. And then we can check how our driver responds in situations staged at Castle. However, right, those things are also great, but it's also quite effort intensive and requires a lot of thought how to set up these scenarios. That leads us to simulation, right? And simulation at Waymo is used extensively for validating the performance of new releases at scale. Simulated scenarios do not really expire too, and so you can use them to evaluate successive versions of the stack. And of course, simulation can provide important supervision signal for machine learning algorithms. Now, before we continue talking about simulation, maybe one way to look at it is to say, well, what do recent DeepMind AI successes have in common, apart from the fact that a lot of really smart DeepMind AI people do great things, right? Well, you know, there is various systems of theirs benefit from learning how to maximize rewards at scale by running millions or billions of simulation for the task at hand. And achieve really great result doing it. Now, the question for us is, right, well, where is the perfect self-driving simulator? First, we need to build that simulator, and then we need to use it to define and solve the autonomous driving stack. Right, so that's great. Right, so what do we want to build? We want to build a simulation city. And this is a picture from the SimCity game, for those that don't recognize it, as a symbolic representation of a simulation city. Right? And the purpose of the city would be to train autonomous vehicles so that they can learn much faster from simulation than from real-world driving. And you want this city to be built on your data that you've collected from your 20 million plus real-world miles driven and benefit from the experience. You want to do, if possible, full trips in all kinds of environments and traffic. You want ideally to take all kinds of scenarios, situations encountered in the real world and replay them in each real world scenario up to 10 or 100x different ways with agents, right? And so this project is ongoing at Waymo. We're exploring Simulation City. One key prerequisite for this is, all right, simulation realism. Simulation realism is important because you want the outcomes in the simulator in the real world to be highly correlated. The more there is a discrepancy, the more you need to reconcile it with this gap with human expert inspection and judgment. So the more you can minimize it, the more you can just purely rely on simulator driving. And so perception realism, so simulation realism has several aspects, and one is sensor or data or perception realism. So first, we need to, if we drive in the simulator, we need to be able to simulate the vehicle sensors, or at least the outputs of the perception stack. I mean, ultimately, it depends how you design your system, but one of the two. And Waymo has a key advantage in this space because we have powerful 3D sensors. We can reconstruct the environment with really high fidelity, and the background of this image is an example of a Waymo centimeter accurate map reconstructed with our lidars. And of course, we also have very powerful perception and auto-labeling algorithms to reconstruct very accurately the movements of the dozens or hundreds of agents, as I showed you in the scene. And so, based on these environments, you can run simulation, and of course, we do a lot of simulation of all our sensors, LiDAR included. I will show camera simulation because I think people can relate and have the most intuitions about it. So here is a scene we drove in San Francisco, and we have a reconstruction of it. It's on the right half of the image is a simulated camera output. And so if you look closer, the shadows for the building and the light poles, right, will start aligning because one is reconstructed, the scene is reconstructed based on what we detected. The vehicles are placed where we detected vehicles, poles and lights are placed in the locations where our perception system detected them, right? And the buildings will average from Google Geo, who have gone with efforts like Street View, collected data and reconstructed nice models of the buildings in the scene, right? And so then we can continue playing the same scenarios in different conditions. So you can play the scenario in the fog or in the rain, or you can keep changing the time of day. And that allows you to multiply your learnings and experience from these scenes. So that's one simulator that was based on more traditional 3D reconstruction type of techniques. But in this next video, I want to show you some early results that we're getting in collaboration in Google Research on building a large-scale simulation environment that is generated by a trained machine learning model, right? And so this is a learned model showing the simulation environment. And here we gave a trajectory that is very unrealistic, that no vehicle can drive, just to prove that this is a simulated environment, because we fly through vehicles and parking lots as we go. But this kind of tells you the fidelity that is possible by using machine learning to build a simulator. And so I'm very excited about this direction. In addition to reconstructing the scene, you can also reconstruct various vehicles that you observe in the scene. And these are some I'm showing with fairly complex shapes that we can then pan around and show you quite realistically how they change. And so this is still a bit early work, and there's room for improvement here, but I think it's quite promising. Let's move from perception realism and sensor realism to behavior realism, which actually potentially is even more important. And this is my classic example that I show and motivate the need for behavior realism. So this is a scenario we captured at some point when the Waymo vehicle was the green box, and it drove through the scene and recorded how a set of objects behaved. And now we start driving in the simulator and do something different, and we end up being the cyan box. And so if we naively play the other agents the way we collected them, they start, well, pretty much smashing into us because, I mean, in the new environment, they're completely unaware that we are now in this new position, right? And what is needed is these agents themselves, they react to the things we do, and we need to build the world, the simulator. The moment we deviate a lot from what we did when we initially captured the scenario, we need to build a simulator where the agents react to our behaviors in a realistic way, right? And we have been building agent models at Waymo even from before I joined it, so 3 years now. we have a variety of different simulated agents based even on different models. Here, I decided to show you a couple of our recent fully machine-learned agents. So these 8 green objects are all embodied by our agent model. And you can see the vehicle here decides to merge well, let's first 2 vehicles pass, and then it decides to merge. And it starts going for this lane, and they come to an interesting situation, which is kind of the type of things you want to test. On the bottom is the same starting condition, but this time the vehicle just merges really quickly, and a completely different scenario ensues, right? And this, I wanted to illustrate with this the power of agents to multiply your learnings. Even in a single scenario, you can play it 10 to 100 different ways and check them what happens with your own autonomous driver, how it will handle them. And now that you've seen examples of our agents, the question is, okay, well, what is a good objective for behavior realism, right? And one criterion for realistic behavior is when you observe it, like in the example here, can you tell that it's actually an agent versus the real thing? And so here, one of green and blue is the real thing, and one of them is an agent that we have replaced the real thing with. You can try to guess which one is which, right? And humans are quite good in a specific instantiation of a scenario to tell you what is realistic and not. However, they also doesn't quite tell you about the distribution of behaviors, the full distribution. And so for this, you can use distribution matching metrics to measure how certain aspects of the agent's behavior, such as, for example, how often it runs off-road or how often it collides with other objects, whether that's realistic compared to the expectations we have. And it's a very complex distribution generally of agent behavior, but you can slice it along verticals that you care about specifically and that relate to your safety expectations, for example. Or, you can check that the accelerations and the amount of turning and cut-ins an agent does matches what you see in real scenarios. But these examples in a way to ground the development of agents into reality. And planning agents are quite related by design. Typically, a planning agent is given a route and tries to execute it. This is an example of a fully learned planning model that navigates quite successfully. I'll play it again. Narrow environment. Here they're doing negotiation with this agent, and then later our vehicle will stop and let the other agent pass. And for AlphaSim agents, imitation and realism is what you want. For planning agents, we need to go beyond the imitation level of performance, which presents an interesting opportunity to start combining imitation learning with reinforcement learning, right? And here's an interesting type of agent that I'm showing you here, of the kind that we train in our simulators. So let's zoom back out and see how some of this discussion fits into the big picture. So ultimately, when you build AI agents, you can use ML to pull yourself by the bootstraps. And so the process looks a bit like this. So we go and collect data in the real world with our platform. We build a simulator and with that data. And we also use imitation learning to learn simulated agent models and populate the simulator with such models. Then we can train in that simulator and also leveraging real-life experience an autonomous vehicle model. We can evaluate it. Potentially, you can also leverage some humans in the loop. And then once we have AV models we like, we can go out in the real world, collect more data with these models, and close the loop. And so we are actively working on setting up and iterating this virtuous cycle. And I look forward to sharing our ongoing progress on these topics in future venues. Thank you very much.